Okay, and
Yep, go. Let's.
Your entire screen 2. All right. Can everybody see the presentation?
Yep.
All right, perfect. Okay, so hello everybody. My name is Xavier Attendu, and I'm going to be presenting a little bit on fibers and guided optics and how that's relevant for biomedical optics at large. So very quickly, tiny little bit about me. I'm a PhD student working also for Professor Faber at the Amsterdam UMC, or previously AMC. I'm originally from Montreal, and I'm doing a joint PhD between Polytechnique Montreal and the AMC. My work is about basically multimodal OCT. So you guys have learned about OCT in your previous classes. And all of my research is centered around taking OCT and adding something extra onto it to enhance its capabilities in terms of detection of disease, specifically cancer. And some of the things that I do are, and this is all very fiber-based, hence why I'm giving this presentation here, where we use these special type of fibers to do these combinations, to add a spectroscopic channel, to add color imaging, and all of this in endoscopy format. And you'll see throughout the presentation that that fiber optics are highly relevant in this. So yeah, so briefly, how this is going to go today. So I'm going to start talking about waveguides. So I'm sure you've all heard and seen optical fibers, but before we go into the fiber geometry, we have to understand how light is guided through different structures. And waveguides covers all of these structures, whether they're cylindrical waveguides like fibers, but they can also have different shapes and forms. And so to understand a little bit the theory behind it, we're going to start with a general waveguide. Then we're going to talk a little bit more into detail about fiber and how that works, and talk about or give an overview of some of the key fiber components that you may have to use if you end up doing research or industrial work in biomedical optics. Then we'll talk about some of the applications of fiber in biomedical optics. A little bit of focus on these three, but they are just three examples amongst many. And finally, we're going to talk about a larger assignment that will be due. I'm not sure exactly the deadline. That's something that Dirk and I will have to set. But you'll have a team assignment where the assignment will be about experimental design. So my expertise is a lot more engineering than science, and there is a big distinction where science is understanding the phenomenon and predicting what's going to happen, and engineering is, said in a very simple way, making things work. And those two go hand in hand when you're working in biomedical optics, because you have to understand the underlying theory that, I apologize for the noise, the neighbors downstairs are drilling into the walls. It's not ideal for giving a class, but hopefully it won't last too long. So what I was saying is that in biomedical optics, you have to understand the underlying phenomenon of how your light interacts with your sample, and also how the technique works. So, for example, the interference phenomenon in OCT, the absorption or scattering that may occur if you're looking at some microscopy technique, or perhaps if you're doing treatment, how ablation works and that kind of stuff. So those are all the physical concepts. But in order to apply that in biomedical optics, you also have to make sure that all your components work well together. And so this assignment will be in teams of 4 or 5, and you'll be asked to design a system, and then I'll challenge that system, and it's going to be a little bit of engineering, a more engineering approach, but we'll discuss that further later on. Okay, so guided optics, the very beginning. So the whole of guided optics, oh, by the way, if at any point something is unclear, don't hesitate to speak up and ask a question. So let's make this a little bit more interactive rather than just me speaking by myself the entire time. So the whole field of guided optics at its core is all about a phenomenon called total internal reflection. So total internal reflection is what happens when light bounces at an interface between two materials that have different indexes of refraction. And there's a specific angle at which this happens where none of the light is transmitted through the boundary, and all of it bounces back. And it was first demonstrated by this man, John Tyndall, but it was independently discovered by Newton, Huygens, all the famous optics scientists. And perhaps one way to see it that you've probably seen before is this experiment, where a laser beam is passed through a little bit of a stream of water coming out of a hole, and you see that the laser beam is staying inside the water. So how does that work? I'm sure you've all seen in school previously Snell's law and how to calculate how a ray of light is going to be transmitted and reflected at an index interface. So Snell's law, very simple, is n1 sine of the incidence angle. So that's the angle between the normal to the interface and the ray of light. And this law allows you to predict the angle at which it will come out. And if the two materials have different indexes of refraction, the index will be different. Hence, the light will bend. Okay. So if you gradually increase the incidence angle, so the angle between the red beam here and the normal straight line, there's a moment where the angle of transmission, the refraction angle, will go to 90 degrees. And that doesn't really make sense because at that point, the beam isn't actually being transmitted through the interface, it's traveling parallel to the interface. And that's called the critical angle. And once we hit or we exceed that angle, essentially the phenomenon of total internal reflection occurs, where none of the beam is actually transmitted and all of it is reflected back to the initial material. Now, in order for this to occur, the condition is that the index of refraction of the initial medium is higher than the index of refraction than the other medium. Okay. Another way you can see this, for those who like this, is that the momentum of a photon must always be conserved. And if you look at it, there's a moment where this is that analogy. Anyway, so planar waveguides. So now let's imagine the simplest geometry. So we don't have a fiber yet. We just have a slab, an infinite, a one-dimensional slab. So it's infinite in both other directions, where the index inside these boundaries, inside these two row boundaries, is a certain value, and the index outside is another value. So in this presentation, I usually call the index in the middle the core index, and everything outside is the cladding index, and that comes from fiber terminology. But yeah, you have the core index inside and the cladding index inside, and this core index can be a unique value, but it can also be something that has a certain profile. And so if you look at it in this 2D representation, typically what we have is we have the X or the Y axis, which is vertical, and then the Z axis, which is the horizontal axis. And we always assume that the light is traveling horizontally through this slab. Okay, so what is the first and simplest type of waveguide is called the step index waveguide. So this is inside the waveguide, you have the core index, which is a unique value, and outside you have the cladding index. Now, if we send a beam of light towards the interface, so gray area, core index, white area, cladding index, if we send a beam of light towards this interface, we can use Snell's law to predict how the light is going to interact. So if we are at an incidence angle here, the theta I, which is smaller than the critical angle, then there will be some light will be transmitted through the interface and out of the waveguide. Okay. If we exceed the critical angle, then all the light stays inside the waveguide. And so that is the fundamental of a waveguide is when all the light remains inside the waveguide, your light is called you call it guided light. So no matter how far along in the z direction you go, the light will always stay inside the waveguide because the angles will never change. So if you do simple geometry to show that if you just bounce this back and forth, the angle of incidence here is always the same. Okay? So the light will, in theory, travel infinitely inside the waveguide. So far, so good? Okay. So just to be clear, when I use the angles, theta I here is the incidence angle at the interface. So it's the angle between the ray of light and the normal to the interface, this little blue line. Throughout this presentation, I'm going to use the input angle a lot, theta Z, or the angle of the beam, which is the angle relative to the optical axis, which is the Z axis. Okay? And so the relationship between theta I and theta Z is just 90 degrees. So it's theta Z is equal to 90 minus theta I, or vice versa. And that's why here the critical angle is defined as the cosine instead of the sine. Okay, so if we go back to this equation right here, can you see my mouse, by the way? Okay, perfect. So this angle is defined with a sine because that's defined that's the critical incidence angle, and here this is the critical input angle, so this one right here. Okay? All right, so there's some very straightforward equations that predict how light is how much light is transmitted and how much light is reflected. They're called the Fresnel equations. And basically, yeah, there are these equations that depend both on the indices of your two materials and the angle of incidence, and depending also on the polarization. And when you're working with unpolarized light, it's simply the average of the two. Now, let's say that I have a beam that's traveling with an angle that is within the critical angle or above the critical angle. There will be total internal reflection and there will be no losses. Okay. If your light does have some refraction, so you're outside of the total internal reflection regime, your light is not guided. At every single bounce here, you will have some losses. And the reason why we usually say that light is not guided is that even if these losses are very, very small, so let's say you're very close to this critical angle, and the losses will be very, very small, but waveguides are usually also tiny, tiny, tiny. So these bounces occur, like the distance between here and here is very small, meaning that if you have, I don't know, 1 meter of fiber or a 1 meter waveguide, the light is going to bounce a huge number of times. And then your loss, let's say you're losing 1%, it's 1% at every single bounce. So the remaining light is 0.99 to the power of the number of bounces, right? And when that number of bounces gets really, really large, as it does, then you're just essentially losing all the light, which is why we say that the light is not guided. In the end, if you do 0.99 to the 1,000th power, that's basically 0. Okay? So guided light, not guided light, is okay for everybody? All right. Okay, so in waveguides, we have all these angles, we have all these indices, and one of the ways to describe how to describe a ray and to determine whether or not it will be guided is something called the ray path invariant. So it's this value called the ray path invariant or the effective refractive index. And that's used to determine the propagation constant. So this is a value that is always the same no matter where you're at in the path of the ray. And this number, it fully characterizes the ray, so you can calculate everything that happens in the waveguide based only on this number. Now, this is just like the language that people that do guided optics use, and depending on which type of waveguide, there are a certain number of invariants. So for example, for a 1D waveguide like this one, there's a single number. For a 2D fiber, there are additional values necessary to characterize it. Okay, so the ray path invariant is characterized in this case by the cosine of theta z. So once you know this value of theta z, you know everything you need to know about the ray in order to determine whether or not it will be guided. How long is it going to travel inside the waveguide? How fast it moves, how long it takes, the optical path, and so on and so forth. And so what you see here is that when you calculate the ray path invariant, you can right away tell if the ray is guided simply by seeing if that value, so this value is the ray path invariant or effective index, is between the core index and the cladding index. If you have any value outside of that, then your light will not be guided. Okay? So basically, any value above the core index is not possible, and any value below the cladding index will not be guided. All right. So some of the interesting things that you can figure out using the invariant or the effective index is, for example, the geometric and the optical path length. So it's quite simple to see that if you have the most simple ray, which is a straight line down the middle, that ray will not have the same path as a ray that's bouncing back and forth, right? So this ray, for example, has the distance that it travels to get from one side of the waveguide to the other is much larger than the one that travels straight down the middle. Okay? And so you have these values. So the geometric is just the physical distance that it travels. The optical path is this physical distance multiplied by the index through which it's moving. So in this case, it's always the core index. Propagation half period is the distance between two bounces. Between one bounce here. So from this position to this position in Z. And the number of reflections per unit length is simply 1 over the inverse of that value. Okay, so you have these different path lengths, and one of the important things to understand is that because of that, the group velocity is different. Meaning that if you send a beam along the center path, the speed at which it travels through your waveguide is not the same as if you send it at a certain angle. Okay, and this is very important because if you're using, for example, pulsed light, and you send it down and you're trying to measure very precise timing signals, depending on which angle you send it at, well, the timing is going to be slightly different, right? And that is something called modal dispersion. So every single angle at which the light can be guided, so there's a certain range at which that can be guided, is called a different mode. So it's a different way that the light can travel in your waveguide. And modal dispersion is the process by which different modes travel at different speeds. Okay? And then finally, this group propagation time is just the time it takes to travel a certain distance. Okay. little bit more information. So the index of refraction also varies with wavelength. Therefore, if you have variation of the index of refraction, you're also going to have variation of the propagation time. So this optical path length, the group index, group velocity, those are all going to change as the index of refraction changes. And therefore, if you send two pulses of light with two different wavelengths at the exact same time, they're not going to come out of your waveguide at the exact same time. And that can also be an important effect for different applications that we'll talk about in a second. And so the you've studied, I think, the Kramers-Kronig relationships and the how you can do a theoretical analysis of the index of refraction and how that varies as a function of wavelength. In practice, so we have these. In practice, what we actually do is we often use these Sellmeier equations. So the Sellmeier equation is an empirical formula that tells you how the index of refraction varies with wavelength for all sorts of different materials. Yeah, and then here I give you one useful tool if it ever becomes relevant, as it will in 2 seconds. If it becomes relevant for you to calculate certain indexes of refraction, that's a great tool because all of the it has a huge amount of data for all the optical glasses, but also for normal or for common materials such as ice, water, yeah, fats, certain types of metals, but metals are not so relevant here. And so the reason why it's going to become relevant in a second is I have a mini question for you. Okay, so consider the following. So you have a planar waveguide that has a diameter of, a thickness of 100 microns. The core is made of one type of glass and the cladding is made of another type. And this waveguide is 100 meters long. Now the question is, for which wavelength range is it possible for light to be guided in this waveguide? The next question is, if you send a pulse of light, which is 10 picoseconds long, it's a very, very short pulse at 1500 nanometers, what is going to happen to the length of this pulse at the output of your waveguide? So yeah, well, basically you can read the questions, and what I'd like you guys to do is just take a few minutes and look through the previous through the slides that I am going to actually send right now. Realize I haven't done that. And you try and answer those questions. We're just going to take 10 or 15 minutes. Try to answer those questions on your own, and then we'll see how it works and why this is relevant for biomedical optics. Okay, Dirk, are you there?
Yep.
Okay.
Yep.
Can I send you the presentation?
Of course.
Okay. All right. Or should I post it directly in the chat here? Is that possible?
I don't know. You can try, but mail it anyway. Then.
Okay. Okay, it's sent.
Yep.
If it takes too long, I can also give access directly on my Google Drive.
No, wait.
Is it okay?
Yeah, just a sec. I have to upload it again.
Does anybody have any questions so far? It's very, very simple stuff, but the relevance is coming, I guess, in this mini assignment. You'll see why it's important.
If we have time anyway, I had one question about slide 4.
Yep.
Where you see the light propagation through the little stream downward.
Yeah.
You see the light. So does that actually mean that it's not total internal reflection?
That's a great point. So in all these all this waveguide theory, we always assume total internal reflection, in which case you're exactly right. The light does not exit, and so theoretically you should not see it. There's 2 points in this particular one where why it fails. The first is that the stream of water is not perfectly straight, right? So if it keeps bending and bending and bending, eventually you will hit a point where the light does exit the water. But here, what happens is also that you have inside the waveguide, which is the stream of water, you may have little bubbles or turbulences, which essentially will cause scattering inside of the beam. And so when you have scattering, you saw in your previous classes that the light can kind of go in any direction. And so when there's a scattering event, that the light that is scattered, let's say, completely perpendicular to the stream of the water, that particular light will come out, because then that one will have an incidence that is lower than the critical angle. Does that make sense? And so it's actually a very good point. So in waveguides in general, in fiber optics as well, we're assuming that light is perfectly guided, but the fiber, as soon as it's bent or as soon as it's imperfect, which it always is, so let's say there are small imperfections in the fiber, that will cause a little bit of the light to exit the fiber and to be lost. The difference is that is due to imperfections that can be minimized, such that you can extend the range over which the fiber is useful, or the waveguide in general. It's a really good point, though. Okay, is the file uploaded, Dirk?
It should be on there now.
Okay. So let's take about 15 minutes, try to answer. And if there are any questions, I'm right here. And in about 15 minutes, we'll discuss all together what you guys found.